Yes. Yes, it is next Monday. Okay. All right, everybody. Let's make sure we're clear on schedule and whatnot. So one thing I want to mention, and it's not really so much a big deal in here, but it happened in another class. So I received one of those excused absences emails. You know what I'm talking about? So when you get an excused absence, you file it and whatnot. And it was for another class for an absence on January 10th, and I got it yesterday. So, like, if you're going to miss class, just let me know. You know, it's okay. But, like, now I have to go all the way back from, like, a month ago and, you know, fix attendance. Like, you know, just let me know. It's really okay. So, because here's the thing. If it's excused absence worthy, like, I do think you still need to go through the process. But if you're going to miss class, like you got a job interview or you're not feeling well, just let me know, and I'm pretty easy to get along with. Okay, homework 2.6 and 2.7 are still being graded. 2.8 is due today. 2.9 is assigned today. This is the last homework before the first celebration, and I'm giving you the solution on Friday, so no late submissions, okay? So by Friday at 11, you got to get this homework in. It's pretty short, so it's not too bad. And we have our exam review on Friday. We celebrate on Monday. Everybody good with that? No? Well, we're doing it anyways.
I'm supposed to be filled with love on Monday.
Well, you're celebrating steel design. Like what?
Valentine's, should I go for it?
Well, I'm bringing party favors.
I would prefer donuts over party.
Tell you what, I'll put like a heart on the front page of the exam.
There you go. Just bring us like the little like Valentine's things that have like the little stuff through it.
Yeah. You can come at Dollar Tree. Not a lot of effort.
Things at Dollar Tree are now more than $1, though, right? Fun. Everybody's doing the exam real quick because of all the sugar. have 30 sugar rushes occurring in front of me all at once. All right, everybody. All right. Any other questions about logistics? Everybody good? Okay, I'm going to bring it back to reality, and we're going to begin our discussion of threaded rods with a pretty serious note. I'm curious if anybody in here has heard about this before. Okay, there's a few people that have heard about this. This is a collapse of an elevated walkway that occurred in the early 80s at a hotel in Kansas City. About over 100 people died and about 216 were injured. To date, this is the deadliest, and I say this with clarity, the deadliest unintentional structural failure in American history. And I want to couch that with a little bit of, with some facts so that everybody kind of understands what I'm talking about here. So I'm not putting this into the same category as something like 9/11 or the Oklahoma City bombing and whatnot, because from a structural engineering perspective, they sort of fit into different categories. Let me give you some factoids about the Oklahoma City bombing to kind of put this in perspective. Have you, everybody in here heard about that? So that occurred in the mid-90s. And so in Oklahoma City at the Alfred P. Murrah Federal Building, Timothy McVeigh drove basically like a U-Haul. It was a Ryder truck. It was filled with explosives. He parked it next to the Federal Building in Oklahoma City, and it was filled with explosives, and it went off. To give you some facts to try and understand the magnitude of that explosion, the van was parked next to a support column for the building. And this column, it's a steel column that's supporting a multi-story building. It's huge, you know. Flanges are like this thick. You know, it is a big column. And the explosive impact was so profound that the steel column shattered. Okay? There was broken glass reported in windows from up to a mile away. I'm not making that up. So the point I'm making is there is no way that a structural engineer is going to account for that type of force in a design, right? That just isn't going to happen, right? And we as structural engineers, we kind of don't even bother, right?
You don't plan for bombs?
Well, no. That's a fair question. That's a very fair question. The answer is we do, but not really from a structural design standpoint. Does anybody know? All right, we got a federal building right down the road. How many people here work at the Army Corps of Engineers and see that little row of steel posts that surround the building? We think those are for. They are not there for aesthetics. They are there to prevent vehicles from being near the building. They are threat deterrents. That's what they're for. So we do account for it, but not from a structural design standpoint. So in structural engineering terms, those two events are what we would call extreme events. They are outside the normal day-to-day operation. So the structure failed, but not through normal operation. This is different, okay? This is more akin to what happened in Pittsburgh not too long ago. That bridge failed under normal operating conditions, right? This walkway failed under normal operating conditions. And under normal operating conditions, we had 114 deaths, 216 injuries. And in that instance, it's the worst structural failure in American history, okay? It was a really bad day. Let me talk to you a little bit about what happened so that you understand. So here's sort of a elevation view of the facility. Now, if you've ever been in a large hotel lobby type area, typically the lobbies can encompass more than one floor, right? You have this really big open space, right? Okay. Now the lobby in the Kansas City Hyatt Regency had these elevated walkways. Like you can see one right here, okay? Now the walkway in question was not a single walkway, but it was two, right? And there were at the time in question, this happened on a Friday evening, and the hotel lobby was hosting this like tea dance party event. So they would have like live bands and they'd have music and whatnot. And so there was a lot of people there. There was about 1,600 people in that area because it was kind of like a, I don't know, like a dance club or whatnot, if you were. The fourth floor walkway connection, it failed under the design loads. What happened was the connection right here, if you zoom in, this is what it looked like when it was built, and it used these threaded rods that were supporting the floor system. Both walkways ended up collapsing because this entire connection sheared through. So this walkway fell, and this walkway fell on top of it. So there was like people not only had a walkway fall on them, but there were people sandwiched as well. So it was a really, really bad day. Now, that's what happened. Here's why. I'm currently teaching Engineering 217 and with Tanner Drown. And one of the things that I mentioned in terms of professional concepts, like one of the most important components of good, sound practice as a professional is communication. And I'd argue that we talk about the gross section yielding limit state and the net section fracture limit state and block shear rupture, but there is a communications limit state that we kind of need to make sure that we're paying attention to as well. See, this is how the threaded rod system was designed, okay? This is how it was designed. This is how it was built, okay? The contractor didn't want to deal with these massively long threaded rods that went from the ceiling and had multiple floor beams going between them. He figured it was easier if he just cut the rods in half, and it made handling a little bit easier. He probably saved about $20 per connection. I mean, it was, you know, over 100 people died, but hey, that was like $4,000. You know what I mean? And what happened was there really wasn't a proper conveyance of communication, right? What should have happened is the contractor should have put this idea out there, actually communicated it to the engineer. The engineer should have done the math and realized this isn't going to work and said, no, you can't do this. Or if you are going to do this, you need to beef up the floor beams, you need to change some member sizes, etc. And that didn't happen, okay? I would argue that you could probably trace a lot of the large-scale engineering failures in modern history not to some mathematical failure of engineering theory or some calculation error, but a lot of them through a lack of communication. Something changed, the right people didn't find out about it, and people died. So I don't want to, get, too on the melodramatic side, but I think that's sort of an aside point, but a very important point for what we do as engineers. Okay, hopefully you take that point to heart. Let's talk about the threaded rod component, though, because that's kind of what I want to focus on today. Threaded rods are a very common type of tension member. You are taking a rod and yanking on it. They are also actually fairly easy to design. So let's talk about them. So first off, threaded rods are very lightweight. They are very easy to deal with. They're easy to manufacture. They can serve as sag rods. They can serve as diagonal bracing elements. So I'm curious, how many of you live in the, Ona, Salt Rock, Milton, Malcolm Springs area, or basically have been down Route 60 and seen the Pepsi bottling plant that's been being erected these past few months? How many of you have seen that? You've seen it, you've seen it. If you look in the building, you'll see this big frame, and you can see the diagonal elements. Well, you can't see it now because it's erected and done. But you can see those sort of cable rod elements that were going diagonally. They are intended to make sure that the building doesn't undergo lateral instability, and so they're basically, serving as diagonal bracing. For a building like that isn't very tall, you don't need super stiff diagonal bracing elements. So these are a very common alternative. Now, unlike regular, actually, let me take a step back. So I want to focus a little bit on this. So these are commonly available bar diameters. This is a good rule of thumb. So anywhere from 1/4 inch to 1 1/4, we can spec these out with 1/8 of an inch increment. So like 1/4, 3/8, 1/2, 5/8, 3/4, 7/8, 1, 1 1/8, 1 1/4. We can do that pretty easily. Once we get past 1 1/4 inches, we typically spec them out in 1/4 inch increments. So when we're doing problems, that's a good rule of thumb to keep in your head as you're specking out these threaded rods. Now, unlike regular tension members, as we know, have a gross section yielding limit state, net section fracture, block shear rupture. Really, threaded rods only have one, and it's tensile rupture. See, I have this image here on the bottom and I've really tried to draw this to scale so that you can actually see what's going on. We have a gross area and we have a net area. And the net area is clearly going to be smaller than the gross area, right? And if you look at the amount of area that we reduced due to the threads, which we typically assume is around 75%, and you look at the grades of steel that we use for threaded rods, really you only need to consider a net section fracture. So that's all we do. And because of the nature of the problem, there's really no iteration. There's no assumptions that we need to make. We can just solve for the diameter pretty easily. So let's look at the spec. Now, threaded rods are considered threaded parts in AISC. So they're considered more of a connector element than they are a member. So they're governed by the equations in Chapter J, not the equations in Chapter D, right? So Chapter D is the chapter on tension members, and this is Chapter J. We've already started to dip our toes a little bit into Chapter J already, because we had block shear rupture was governed in Chapter J. We had threaded rods that were in Chapter J. We're going to start to spend a lot of time in Chapter J over the next little bit, because Chapter J2 is the section on welds. Chapter J3 is the section on bolts. And so threaded rods are kind of treated like a bolt because they are a threaded part. And we propose that the tensile strength or the shear strength of a threaded part or a bolt is some nominal stress times some area. Okay. Now the area is pi d squared over 4, so that's pretty easy. But the nominal stress, we have to do a little bit of digging. Now I want to say something about this blue note right here. Sometimes navigating a specification can feel like a scavenger hunt because here's the equation, and then it says, okay, look at the bottom where it says where AB is the nominal unthreaded area, and then where it says FN. Okay, FN comes from table J32. So it's like you find this section, then you got to turn to this section. Then you find this section, you got to turn to that section. That's kind of common in engineering specifications, and so it's something that you kind of want to get used to. I know that that's probably annoying the first time that you start to foray down this road, but trust me when I say that there is a logic and there is a reason why specifications are organized the way they are. It makes it easy to keep track of them and to modify them if you're a governing spec body. So now here's table J32. This is a table we're going to look at a little bit more after the first exam. This is a table that outlines the nominal capacity of threaded parts. So when we look at bolt shear and what have you, we're going to spend a little bit of time looking at this. And so if you notice, the slide looks a little weird. If you turn to page 16.1-129, you will see that the table is actually pretty long. And so I've cut off a fair amount of it because I wanted to sort of focus on the stuff that mattered. In this case, threaded parts meeting the requirements of section A3.4. And you can notice there's two columns on the right. There's one where we're looking at nominal tensile strength and one where we're looking at nominal shear strength. And it doesn't really matter which one that you're looking at. Both of the nominal tensile stresses are listed as 0.75 FU. So that's going to be our nominal tensile strength. And that 0.75 is sort of accounting for that lost lost efficiency due to the fact that you're dealing with the threaded portion, not the gross area. So if we wanted to compute phi RN for a threaded rod, so everybody follow with me on this. I've done some fraction work here to make our resulting equation a little easier. So phi is 0.75, which is 3/4. FNT is 0.75 FU. So this is our safety, our resistance factor, and this is the reduction of efficiency due to the fact that we're dealing with the threads. And then our area is pi over 4d squared. So this times this times this. So we got some fraction work here. On the top, 3 times 3 is 9. On the bottom, 4 times 4 is 16, times 4 is 64. So we can compute the capacity of a threaded rod pretty easily. Phi RN is just 9 pi over 64 times the material strength times d squared. So hopefully that's pretty simple. Any questions on that? Okay, so here's the point. If you want to design a threaded rod, let's look at this equation. If I'm designing a threaded rod, what am I interested in? I'm interested in determining the diameter. Well, if I know the load and I know the material, I just need to take this and solve it for dB. So take most sides, multiply it by 64 over 9 pi, divide both sides by FU and take the square root, and here you go. So basically what I'm doing is setting the load equal to that. So this is the load on the rod. Flip, divide, take the square root, boom. So this is designing a threaded rod. It's pretty simple. So in order to design a threaded rod, we determine the factored load, we compute the minimum bar diameter, and we select a rod. And that's it. Now, as we chug this out, how many limits have we addressed so far for tension members? We've addressed 4 of them. Gross section yielding, net section fracture, block shear rupture. What am I missing? What's the other one? Has nothing to do with the loads. Slenderness, right? Why am I not talking about slenderness? Here's section D1. Are there any limitations on slenderness? Let's read this. Remember how I said for members designed on the basis of tension, the slenderness ratio preferably shall not exceed 300. What does that second sentence read? This suggestion does not apply to rods or hangers in tension. Threaded rods are inherently slender, right? They're not like angles or channels where we're worried about, deformation or cross-section damage and whatnot. Threaded rods are meant to be slender, so it's okay. We don't need to worry about the L over R limit because it's a slender rod design, okay? Now that being said, you certainly wouldn't want to have a threaded rod experience compression because it's real slender, it's going to be real weak. So we're going to look at tensile capacities versus compressive capacities later. This whole time we've been talking about taking a tension member and yanking on it, taking a piece of steel and yanking on it. Pushing on it, way different story. We got to talk about buckling and inelastic buckling, elastic buckling. It's a totally different animal, but that's past exam 2. We'll deal with that later. Any questions? So I want to look at this problem. This is a problem that I wanted to do this last year. I didn't get a chance to because we had the craziest ice storm in the for the past 30 years in our area. So it was, we lost more school due to that ice storm than we did during the initial lockdown of the pandemic. It was that bad. Random factoid if you didn't know that. Remember? We lost a week.
Yeah, you lost a week. I don't even remember looking at the week. We had a week off and then
remember we had a week off and then we had spring break? Yeah, well, you all probably had a break. We were busting it because I had to sort of figure out how I'm going to teach steel design via Zoom with like 1 week. So, yeah, that was the thing. Okay, we're going to select the most economical threaded rod of A36 steel to act as a diagonal brace for this truss. We're going to assume this is a hinge and this is a roller, so we're actually going to have to break out our method of joints, method of sections, truss analysis skills a little bit. Now I got a load here, a dead load and a live load. We got to do some factoring. So really this problem is challenging from an analysis standpoint, not from a design standpoint. You're going to find that the design goes real quick. So let's go here. All right, so a couple things I'm going to write right off the bat. What is FU? Say it again. No. So it's 58. Who said 35? So if it was A36, that would be FU is 36. Sorry, FY is 36. FU is 58. I don't know where you're getting the 35, I'll be honest. I know you would get it from your AISC 15th edition steel construction manual. That's why. Okay. Now, I want to do one other thing. So this is 58 KSI. Let's do something else. I have 3,000 pounds and 7,000 pounds, dead and live respectively. Should I do something with those? I should factor them. So let's do that. 1.2 times, we'll just say 3 kips, plus 1.6 times 7 kips. What is that? 14.8 kips. Do I have a second on that? Okay. So, our governing equation is 8/3 times the square root of PU over FU pi. Like that's how we're going to design the rod. So can we plug and chug right now? When we got an FU, we got a factored load. Can we just go ahead and plug and chug and be done with this thing? Huh? No. You're engineers. I don't want this guess. I want to know why.
We don't have the PU.
What's that?
I thought PU was like different
But why?
There's some kind of factor that you apply to.
No. That's not the problem.
Is that because of the way that
Wait,
the threaded member is not in the same direction as the...
No, I think you're probably making it out more complicated than it needs to be.
Is it because the 14.8 kips isn't actually all on that cross member?
Here's my point. You're pretty much right there. All right, hold on. Let me show you something. Here's the problem that we're dealing with. We have a truss with a factored load of 14.8 kips right here. This is a hinge support. This is a roller support. This is my threaded rod. I need to know what is the force on this threaded rod. I need to analyze the truss in order to determine the tension or compression on this rod. Just because I have 14.8 kips right here does not mean I'm going to get 14.8 kips right here. Does that make sense? It's not a factor of safety or issue or anything like that. It's that you have to actually do some structural analysis. That's crazy, I know. All right. So let's put some dimensions right here. Let's go back to CE 312 land. This is a hinge support. How many unknown reactions do I have at the hinge? This is a roller support. How many unknown reactions do I have at the roller? 1. I have a horizontal and vertical reaction here. Can anybody tell me what's going on with the horizontal reaction? 14.8 kips in which direction? To the left. There you go. So we'll call this AX. And so summing forces in the X direction, we get that AX is 14.8 kips to the left. So we'll call this support A, call this support B. And so if you want, we can name these other joints C and D, doesn't really matter. So I'm asking you, successful graduates of CE 312 structural analysis, tell me what to do. Oh, that breaks my heart. AY and BY do not equal 0. I propose that AY and BY must act in equal and opposite directions. But it is very possible that one could be 20 kips going up and 20 kips going down. I have 3 equations, 3 unknowns. I propose that we sum moments at A. If I sum moments at A, any vertical reaction at A is going to go right through it, right? I have 14.8 kips times 15 feet rotating point A in this fashion. What must happen here is that I must have some vertical reaction here, some BY, rotating in the opposite direction, such that the sum of moments is 0. So 14.8 times 15 is 222. So therefore, BY is 11.1 kips upward. Now let me ask you again. Now, what do we do? Let's look at it this way. Now what do we do? And summing forces in the y direction will yield an AY that is 11.1 kips going down. Right? So we'll call this AY. Call this that. And then now we need to solve for the force in this threaded rod. Could we have avoided solving support reactions altogether? Maybe. We'll talk about that here in a bit. But we could not start with joint D because there are 1, 2, 3 members going through joint D, right? But we can go ahead and analyze joint A, right? Let's analyze joint A. Let's see if we remember what's going on with all this. So here's the joint. We have a vertical member like that, a diagonal member like that. Is that a 3 to 4? That's what? 20 foot over, 15 foot up. I have an applied load on that joint of 14.8 kips and a vertical load of 11.1 kips. Then that leaves a vertical, horizontal. So help me out. What do we do? Sum forces in the x direction. So summing forces in the x direction tells me, so let's see, says summing forces in the x direction tells me that we'll call it ADX is 14.8 kips that way. So that's ADX. So if this is ADX, what do I do now? Find the y component. It's been a while since you've done this stuff, right? Bringing it back, right? We use the slope ratio. So we take ADY is ADX times something. What is that something? 3/4. We're solving for the vertical, so we put the vertical number on the top, the horizontal on the bottom. So 3/4. So what is that?
11.1.
Say it again.
11.1.
11.1. Do I have a second on that? So if that's the case, what's going on with AC? It's a zero force member. Do you remember the rules with zero force members? Look at joint C. There are no loads applied on joint C, and there are 2 members framing into joint C. That means that this member and this member are zero force members. We use Pythagorean theorem for this one. What's the axial force inside this member? 11.1 kips in compression, right? Bringing it back, right? So what is the force in member AD? And how did you do that? And is that tension or compression? Tension. So now, let's look at this threaded rod design. What is PU? It's the load on the rod, 18.5 kips. We have FU is 58 KSI. So therefore, and what do we get when we chug this out? We'll say like 2 decimal places. Because that's 2 or 3 decimal places is usually enough. 0.85. Do I have a second on that? What does that mean? That's the size rod that we need. So are you going to go to a steel supplier and say, I need a rod that's 0.85 inches in diameter? What are you going to ask him for? And what is that? 7/8. Use what do you think? Is that structural analysis stuff that we did last semester, is it starting to mean something again? You're like, we didn't care about it before, Dr. Mike. We just wanted to get out of your class. What's that?
I've learned you trust this 4 times, but they still don't make sense.
This didn't make sense?
I'm confused on how it's intentioned.
Well, because here's the joint, the forces are yanking away from the joint.
Well, then wouldn't they be pushing on the other joint?
No. On the other joint, they're yanking away. Hold on. Hold on. Forces are in equal and opposite direction. Grab that pencil. Grab it on the end. Hold it out to me. No. Like that. Okay. You're pulling that way, I'm pulling this way. Equal and opposite.
Oh, okay.
The rod is responding in the other direction.
Okay, that makes sense. Good.
It's like you're playing tug of war with it.
Yes, it is like you're playing tug of war with it. So the external forces, so if we go back to the pencil again, so the external forces, he's going this way, I'm going this way. But internally, the rod's not moving. So internally, the rod's responding in the other direction. So that's why internally it's going like that.
Okay.
So
If I took a samurai sword or lightsaber and sliced it in half, you both fall.
exactly, right. So cut, we both fall in because the rod is pulling us together. So the internal forces are pulling together. So make sure everybody understands that because we have time. This is good stuff. So yes. So
Question for you.
hold on.
Okay,
So here's a tensile load, right? Samurai sword. What's happening is we're yanking on it. The rod is responding back such that each free body is in equilibrium.
Okay.
That make sense?
Yeah.
Somebody else said something.
I did.
Yes.
So, I think I'm just looking at this wrong.
Okay.
Since it's in between 1/4 to 1 1/4, you add 1/8 of an inch, right?
No, you don't add.
Wait. What?
That's what I'm confused about.
Hold on.
Go to the next highest color.
The next highest one, right? So, All right, hold on. So 1/4 to 1 1/4, here's what that means, okay? Here's what that means. If I go to the store and I try and buy threaded rods, I'm going to have 1/4, 3/8, 1/2. See how it's jumping in an 1/8 of an inch increment?
Yeah.
3/4, 7/8, 1, 1 1/8, 1 1/4, right? Past that, it starts jumping in 1/4. You see what I mean?
Yeah.
So my question in this problem was, which one do you use, right? So are we going to use this one? No, because it's 0.75, right? We need 0.85, but this one is 0.875. So that's the winner.
I thought you added an 1/8, and I was like, what?
No. I'm at Lowe's going, which one do I need to buy? I need to buy this one,
Okay.
basically. Although it's not Lowe's, it's a service center, but it's kind of the same thing. Does that make sense? All right, I do want to show something before we call it, but I want to ask if anybody has any questions. Because I want to show you your homework assignment, because I want to talk a little bit about it. Yes?
Like tabs that we should know, that like any more tabs that we should be putting on.
Not for this. And on the exam review slide that we talked about on Friday, I'm going to list all the ones I think you should put. I don't think I have them in the slides, but I'll tell you, like, here's the ones I think you need. All right, any questions? Okay, all right. I want to show you something with your homework assignment before we call it. Let me use my mouse. I was trying to use my pen, but it didn't work. So this is the homework assignment. Look familiar? What's that? Well, we're going to design the threaded rods to support this walkway. So a couple of things. Let me zoom out a little bit. Okay. So the walkway is 6 feet wide, and the rods are spaced 20 feet longitudinally. So imagine the walkway goes on forever, and each of the rods are 20 foot apart, right? So what you need to do is treat this like a tributary area problem, right? So the walkway is supported, or is being subjected to a 100 pound per square foot live load, right? So you need to determine the amount of live load on each rod, okay? For the dead load, this floor system is a 4.5 inch thick reinforced concrete slab. Concrete weighs 150 pounds per cubic foot. So what is the volume of concrete that each rod must support using a tributary area concept? Does that make sense? So you've got the concrete supplying dead load, the 100 PSF supplying live load. Once you factor it, plug and chug. But hopefully you recognize the problem. Well, the walkway. Yeah, that's the point. Yeah. What's that?
What's designed, right?
Yeah.
Who got in trouble for that? I guess the contractor. I'm guessing it would be
Everybody that touched it. I honestly, yeah.
Yeah, there was also, on that same, on the Ohio agency, there was also another failure that happened during construction.
I think, but it wasn't as bad as this. Yeah. I think I knew that. I mean, usually, like preparing for this, I'm just looking at, the big deal. But yeah. But I do know that in general, I think there were some maybe questionable contracting practices on this project, which, I mean, it is something to generally watch out for. And it's nothing against contractors. I mean, contractors, by and large, are doing everything just fine. But there is I said this at the beginning of just about every lecture I've ever given, that there's a tightrope between safety and economy. And contractors are out to make money, So those two items come into conflict with one another, and you just have to be diligent, both engineers and contractors. So, any questions? All right, one final thing. What are we doing on Friday? Remind me. So what do I usually ask for the exam review? Come prepared with questions, okay? Now let me say one thing. I'm going to go through the format of the exam. How many times have y'all had me for class? It's not going to be any different format than it has been in other exams. It's going to be very much like the structures exams and statics exams that you've had before in the past. The only difference is we're going to do it in paper. So it's going to be like, you know.
Will we still be allowed to use our
Yeah, we're going to do that. Yeah. So.
Will we still be allowed to use our laptops?
Yeah, we're going to do that. So. Yes.
Is it open notes?
Huh?
Is it open notes?
Yeah, that's what I'm saying. Yeah, that's fine. I don't have a problem with that. So. It's just not open neighbor or open Google Chegg forum. Let me tell you one thing. I'll say this and I'll let you go. So when we were operating this class virtually, I did have a few people using Chegg for the homeworks, but what ended up happening was it was kind of easy to catch them because they were using methods and specs based on stuff we were doing in the 70s. So I'm sitting here looking at their homework. I'm like, one, I never showed you how to do that. Number two, it's not in the manual. Like, I know where you got it. It's from a manual from 1968. You know, it's not right. You know, so what I'm telling you is that, like, steel design, and this happens a lot with a lot of the sciences that we learn in engineering. They change. They're mutable, right? ACI, the concrete spec, comes out like every 3 years. The steel spec comes out every 6 years. The MUTCD, how often does that change? ASTRO changes. So if you're using Google or Chegg or something like that, you are most likely using some old version of the spec that's wrong anyways. You might as well just do the problem. Yeah.
When's the new steel manual coming out?
How many years is the 15th?
Actually, I want to say since 2016.
No.
Let me say two things. One, if you actually go and do steel design in your career, your employer will most likely get you what you need. That's usually not an issue. And two, stuff changes. The ideas don't change. You know what I mean? Like tabulated values for bolts and slip coefficients and factors of safety. That stuff changes. Like, we get more wind data, and so our wind loads change. We get some research project on singly symmetric buckling of girders, and so our models change. But the behavior does. Steel is steel. And that's largely true of everything else. Usually, the stuff that updates from spec to spec is the really new, like, complicated stuff. Like link slabs and simple for dead, continuous for live, and strut and tie modeling for concrete. But basic design doesn't really change all that much. So don't feel like you're getting gypped, because you're not. Besides, well, the only thing I will say, I don't like, the last manual had this like burgundy red. I thought it was prettier. So that's just me. So.
I also don't like the blue color.
I don't. I don't know what the next color is supposed to be.
Well, like, I had,
The last one looked like the red on his sweater. I thought the top of his sweater. I thought it looked good. So.
It's like a medical manual.
It does, like a DSM or something. So, all right. Any questions? That's all I got. I will see you all on Friday.